Hello everyone. So, I was discussing different time inconsistent behavior in the previous module. This is the 48th lecture of the course on principles of behavioral economics, and I am going to continue with such discussion while trying to introduce the concept of naive hyperbolic discounting. So, we begin with an example again to show time inconsistent behavior among individuals, and then present a model which may try to explain those behaviors which are not actually explained by DUM, or DUM is incapable of explaining them. The food stamp program was originally introduced in 1939 as a way to alleviate hunger in the United States. Now known as the Supplemental Nutrition Assistance Program, or in short SNAP, the program provides each participant a card that can be used to purchase food, much like a debit card. Recipients receive a monthly transfer of money to their account, generally on the first of the month. Thereafter, they can use that money for buying food. Close to 50 million Americans collect SNAP benefits to pay for at least part of the food budget, with a cost of over $75 billion per year. The average food stamp recipient does not spend some of her other income in addition to the SNAP benefit each month on food. This finding was originally considered a sign of an effective program when discovered by economists. Suppose that recipients receive some amount of money, say S, in SNAP benefits that must be spent on food. If this then resulted in recipients spending exactly S on food, the restriction on spending of SNAP benefits is clearly binding, and the recipients would have been better off if they had just been given cash they would spend on anything. Alternatively, if they spend K, which is greater than S on food, the rational model implies that recipients could not be made better off by giving them cash instead, because whatever is being transferred, they are already spending more than that. So, if they would have been provided cash, then they would also spend it on food only and not on anything else. Suppose a rational person considering her consumption over the month would solve equation 3. This is actually equation 3, where basically this is consumption over a period of 30 days. X is the consumption or purchases of all other commodities, all commodities other than food. So, Vx is the value generated by consumption of those goods and services, and Uct is the utility generated by consumption of food. They are summed over a period of 0 to 30 days, and each utility is discounted by the discount factor raised to the power the time period. So, here x represents all non-food consumption, Vx represents the utility of non-food consumption irrespective of time within the month, Ct represents consumption of food at time t, and Uc is the instantaneous utility of consumption of food per day. The consumer is given income of W, so an income of W is there, and SNAP benefit of S must solve equation 3, the equation that we just discussed in the previous slide, subject to two constraints, constraint 1 and constraint 2. The constraints are, first of all, the consumption on food over 30 days period should be greater than equal to the SNAP benefit represented by S. And the second constraint, so this is my constraint 1 and this is constraint 2. The second constraint is that an individual's overall expenditure, so expenditure on X and this is the expenditure on consumption, must be less than equal to the SNAP benefit plus the income that he or she receives, W, in order to satisfy the constraints imposed by SNAP. So, basically an individual must solve equation 3 subject to C1, C2 in order to satisfy the constraints imposed by SNAP. The constraints C1, they are reproduced here. So, C1 tell us that the recipient must consume at least her SNAP benefit in food. If she is spending more money than just the SNAP allotment on food, then the constraint is not binding. In the sense, whether we have this constraint or not, it actually does not matter. The constraint is not binding. That is the case when Ct is greater than S. The constraint in equation 2, that is C2, tells us that she cannot spend more money than she has on hand for food. If instead the government simply gave the recipient S in cash that could be used for anything, the recipient must solve equation 3 subject to equation C2, eliminating the food restriction contained in equation C1, because as we are trying to say that this is not binding. But if C1 was not binding under the SNAP program, then the cash transfer result in exactly the same optimization problem as the SNAP program, because the individuals are anyway spending as much on food as they are receiving from the SNAP program and something more than that also. So, it is not, if it is not binding, then giving them cash or giving them the amount in terms of some cards which should be spent on food only would give or yield the same results. Thus, the recipient would consume the same amount of food and be just as well off as if she had received a cash transfer. Alternatively, if the recipient spends no more than S on food under the SNAP program, then C1 is binding and the recipient would behave differently if just given a cash transfer. This added restriction on the solution must result in a lower level of utility than if the recipient were simply given cash. If this were the case, the recipient could be made better off with a smaller cash transfer, and thus the policy is inefficient. The US government is concerned with the rising number of SNAP participants who are overweight or obese. Encouraging them to eat more than they would with a simple cash transfer could be viewed as counterproductive. Thus, economists viewed the news that recipients spent some of their own money on food in addition to the SNAP benefit as good news. Recipients must be as well off as they would have been with a simple cash transfer, and we are not encouraging excess consumption which might be leading to obesity or overweight problem. The problem all started when someone decided to explore how recipient would react to a cash transfer equal in value to the SNAP benefit. So, basically for some regions an experiment was conducted where instead of giving the SNAP benefit, people were given equivalent amount of cash transfer. In 1989, the US Department of Agriculture conducted an experiment in which they randomly assigned households in Alabama and San Diego, California to receive either the traditional SNAP benefit or an equivalent amount in cash. Although the differences were small, on average those receiving the SNAP benefits consumed about 100 to 200 more calories than those receiving cash. Despite both ground spending, although the differences were small, on average those receiving the SNAP benefits consumed about 100 to 200 more calories than those receiving cash, despite both groups spending in excess of the benefit on food. So, both groups spent more than what the benefit they received, but the SNAP group actually consumed more calories. These two facts together contradict the standard economic model of choice. Later work by Parquet, Wilt and Christine K. Ranney shed more light on the puzzle. They found that for the period they studied, spending on food in the first 2 days after receiving the food stamp benefit spikes to about $5 per person per day. Spending the rest of the month hovers around $2 per person per day. So, in the initial days they would spend more and later on they would spend less. Moreover, they find that for a large portion of those receiving food stamps, the calories consumed per day drops more than 10% in the last week of the month relative to all other weeks, which means that the food consumption or the calorie consumption declined in the last week of month. If we consider the model in equation 3, this is the equation 3 which is reproduced here, and the two constraints we have talked about C1 and C2, we should find a solution that satisfies delta s to the power j u prime Cj equals to delta s to the power k u prime Ck. We introduced Euler equation yesterday. If you remember, for 2 consecutive periods it was like u prime Ct, where u prime refers to the first derivative of the utility function with respect to consumption in period t, and u prime Ct plus 1. We considered the ratio of them, and that was equals to 1 upon 1 plus r. Alternatively, if we consider greater number of periods, like if we have this is Ct and this is Ct plus 3, then we might be having here delta square, because 1 delta would be here and delta cube would be here. So, something cancels out. Ideally, this is the marginal rate of, this is the marginal utility of consumption in period j, and this is the marginal utility of consumption in period k. So, the neoclassical analysis tells us that the marginal utility of consumption should be same across all the periods. Accordingly, we have this equal sign. Here, as I already told, that u prime c is the instantaneous marginal utility or slope of the instantaneous utility function evaluated at c. People tend not to discount too much over short periods of time like a single day. So, delta should be close to 1. In this case, equation 4, this was our equation 4, says that for any two periods j and k, if they are relatively close together, Cj should be relatively close to Ck. Suppose j is less than k, the farther they are from each other in time, the greater will be the consumption in period j relative to period k. So, more consumption in the recent period compared to a farther period. This is commonly referred to as consumption smoothing. In the sense, when they are close by, then there is not much difference. Differences are observed only when the time periods are far apart. So, here we introduce this line. This is the usual utility function, and what it shows is that if the discount factor by day is almost equal to 1, the marginal utility function for one day should be almost identical to that of the previous day. So, here we have, this is d raised to the power minus j k, and this is d raised to the power minus j minus 1 k. So, the slopes are pretty close and the consumption are also pretty close on those 2 days. So, this leads to an optimal level of consumption that is almost identical. So, these two consumptions are very close to each other. Here the curve you see represents the instantaneous utility function with familiar increasing but concave form. This kind of utility functions were introduced while discussing prospect theory. This is only in the domain of gain, so we do not have the lower portion. The solid line in sloping upward has slope delta raised to the power minus j k, where k is some constant representing the slope at the optimal time, optimal level of consumption in period 0. So, this is the line slope delta raised to the power minus j k. This line is tangent to the utility curve at one point C j, representing the optimal consumption at time period j. Optimal consumption in the next period occurs at the line when the slope delta raised to the power minus j minus 1 k represented on the graph by c plus c j plus 1. Given the slight change in slope between these two lines, the amounts of consumption should be rather close together. Alternatively, n periods after period j, so this is like delta raised to the power minus j minus n k, which may be very different from consumption in period j. So, you can see that the tangency is here. So, this is quite different from the consumption in period either j minus 1, j plus 1 or period j. In any case, consumption from one period to the next should not change much. That is the basic point here. It should decline somewhat, but the rate of decline should create a smoothly declining function. Alternatively, in the SNAP data, we observe a sharp decline in food consumption in the last week. This signals yet again that the behavior is contradicting the standard economic model of choice. The rational model suggests that recipients will have the foresight to conserve their money to consume similar amounts every day rather than consume a lot up front and then run out of food and money in the last week of the month. So, these are basically not for very rational individuals. Rational individuals would actually conserve their money to consume similar amounts every day. A time consistent model of decision making would not predict this behavior, nor can it be reconciled. So, that is why we bring in the concept of naive hyperbolic discounting. So, we would be introducing or always having this term naive in the sense that this hyperbolic discounting has already been introduced in the last module. So, these hyperbolic discounters are actually naive. So, they do not know that they are making irrational decisions, or maybe making decisions that are not considered to be perfect or rational by some understanding. Robert H. Strauss first proposed a model of time inconsistent preferences due to discounting that varies by the time horizon. Generally, he examined cases in which discount factors delta in the near term are relatively small, indicating that consumption now is much more valuable than in the near future. However, discount factors in the distant future are much closer to 1. George W. Ainsley proposed a model that with some later modifications is commonly called hyperbolic discounting, which replaces delta t, the discount factor, or delta raised to the power t, with hyperbolic discounting factor, where the discount factor is written as 1 plus alpha t raised to the power minus beta upon alpha, where alpha and beta are both greater than 0. The consumer maximizes here consumption stream C1 to C2 to any number of days, the total utility generated from the consumption, that is equal to, this is the discount factor multiplied by the utility associated with each time consumption. Here I equals to 1 to t. So, as you can see that for I equals to 1, I will be having alpha plus 1 plus alpha raised to the power minus beta upon alpha. If I equals to 2, then my discount factor will become 1 plus 2 alpha raised to the power minus beta upon alpha, always multiplied by the utility. Similarly, we will be having for third period, fourth period, and so on. So, time appears here as a in multiplication form with alpha. Now, consider two questions. Would you rather have 1 apple today or 2 apples tomorrow? Would you rather have 1 apple 1 year from now or 2 apples 1 year and 1 day from now? So, here this is like a choice between today and tomorrow, and here it is a choice between 1 year from now or 1 year 1 day from now. If the majority prefers 1 apple today in question 1, then utility from 1 apple is greater than utility from 2 apples discounted to the present time. If the majority prefers 2 apples in question 2, then this is a clear violation of the stationarity property. So, in the question 2, if they say that they prefer delta u 366 greater than delta, this is delta raised to the power 365 u 365, then this is a clear violation of the stationarity property, because stationarity property said that your choices would depend completely between the difference between the two time period, which is like t prime minus t, if you remember. So, in both cases t prime minus t is 1 here as well and here. So, if you like it here, then your preference should be the same when it comes to 1 year and 1 day from now. Let psi is the daily discount factor for decisions regarding consumption 1 year from now, and gamma the discount applied for waiting for 1 year. Now, you can see that if people preferred 2 apples after 1 year 1 day over 2 apples after 1 year, then we can say that gamma u1 is less than gamma psi u2, which is like gamma is the discount factor for 1 year. After 1 year you are getting 1 apple, but that is less preferred to a situation where after 1 year and 1 day. So, you first apply the 1 year discount, then you apply the 1 year 1 day discount multiplied by the utility from 2 apples. So, this is now actually greater than gamma u1. Gamma cancels out, and this is my equation 1 from the previous slide. So, 1 and 2 can be reconciled if delta is less than psi, that is the daily percentage discount decreases over time. Hyperbolic discount can accommodate this pattern. The hyperbolic discount rate for period 0, that is today, and period 1 tomorrow would be 1 raised to the power minus beta raised to the power alpha. So, basically if you remember, we had 1 plus alpha t raised to the power minus beta upon alpha. So, if t is equals to 0, we are left with only 1. So, 1 raised to the power minus beta upon alpha equals to 1, and period 1, that is tomorrow, it is like 1 plus alpha raised to the power minus beta upon alpha, that should be less than 1 for any positive value of alpha. Alpha and beta are positive numbers. So, this is less than 1. Larger the alpha, the smaller is delta. Now, the discount that applies to 1 year and 1 year 1 day are, first of all, you can see this is 1 plus alpha 365, this is 1 year raised to the power minus beta upon alpha, and 1 year 1 day is 1 plus alpha 366 raised to the power minus beta upon alpha respectively. Therefore, psi, which is the daily discount that applies after 1 year, would be a ratio of these two raised to the power minus beta upon alpha, and since alpha 366 and alpha 365 are very close to each other, so we can expect that this is approximately equal to 1 and thus greater than delta. In general, the discount factor applied from one period to the next takes the form psi equals to 1 plus alpha t plus 1, as you can see it is t plus 1 divided by 1 plus alpha t raised to the power minus beta upon alpha, the usual one. Now, I come back to or go back to the SNAP example. Under hyperbolic discounting, the maximization problem is, again we are maximizing x and the consumption stream for period of 30 days, Vx, that is value or utility from all the goods and services other than food. Then this is my discount factor 1 plus alpha t raised to the power minus beta upon alpha multiplied by period specific utility summed up over 0 to 30 period. And the first order condition gives us 1 plus alpha j minus raised to the power minus beta upon alpha multiplied by u prime c j, again the marginal utility of consumption in period j, is equal to 1 plus alpha k raised to the power minus beta upon alpha u prime c k. So, this is exactly the same as that we obtain from, say, discounted utility model. There we had delta j u prime c j equals to delta raised to the power k u prime c k. Here, instead of delta j and delta k, I have these as the discount factors, the rest remain the same. We have previously proved that gamma 0 1 is 1 plus alpha raised to the power 1. So, basically when we are considering two periods, say gamma 0 and 1, the 1 for 0 will be in the denominator. If you just remember, when we are considering simple gamma for the 1 year 1 day, then it was like alpha 1 plus alpha 366 divided by 1 plus alpha 365 raised to the power minus beta upon alpha. So, in a similar fashion, when it is 0 and 1, then I have 1 in the denominator, the lower period or the initial period, and 1 plus alpha, which is basically alpha multiplied by 1 raised to the power minus beta upon alpha, which would be less than psi j k, where we have 1 plus alpha k raised to the divided by 1 plus alpha j raised to the power minus beta upon alpha. This would be, so we claim that psi j k is less than or greater than psi 0 1. For j and k greater than 1, greater than equal to 1, and psi j plus 1 converges to 1 as j gets large. Thus, a SNAP recipient who behaves according to hyperbolic discounting when receiving her benefits will plan to consume a lot today, but then hope to smooth out her consumption over the rest of the month. So, when the days are close by, then he or she considers spending a much larger amount. Unfortunately, a time inconsistent recipient does not live by her plan. Instead, when she arrives in the second period, she solves, like again we have this 30 days, or here now actually 29 days of consumption this is consumption of other goods and services, we are now beginning from t equals to 1 instead of beginning from t equals to 0. And if I have t equals to 1 here, then putting t equals to 1 here, I will be left with 1. So, though this is time period 1, but in order to have a similar flow of discount factors and consumption utility generated by consumption multiplied by the discount factor, I am replacing t with t minus 1 here. The rest of the things remain the same, and the first order condition gives us 1 plus alpha j minus 1 raised to the power minus beta upon alpha. So, initially or previously this was simply alpha j, now this is replaced by alpha j minus 1, and similarly previously it was alpha k and now it is replaced by alpha k minus 1. Consequently, the new discount factor for period 1 and 2 are, period 1 and 2 we have k minus 1 upon j minus 1, which is like equal to 1 plus alpha divided by 1 equals to psi 0 1, but this would be smaller than psi 1 2, where I have 1 plus 2 alpha divided by 1 plus alpha raised to the power minus beta upon alpha. Therefore, previously recipients had anticipated applying a discount of psi 1 2. They thought of applying a discount of psi 1 2 between the first and second period. Now, instead they apply psi hat 1 2, which is psi hat 1 2, which is equivalent to psi 0 1. So, all I want to say is that if you remember, psi 0 1 in case of Terran Matthew example was 30%. And later on it was 10%. So, the recipients of SNAP also first thinks that in the first period they would definitely apply 30%, but from next period onwards they would start applying 10%. But when the next period arrives, then they treat it as the fresh beginning and again applies 30%. Again when they arrive in the second period, then they consider it to be a fresh start and again they apply 30%. So, each period they basically revise their discount rate, daily discount rate, and even though in the initial time they thought of applying a discount rate of 10% for consecutive periods, they end up discounting at a much higher rate of 30%, that is bringing forward consumption to the present time. Higher discount rate implies that individuals are more impatient, they would consume more today, as a result of which in the initial period there are higher consumption, then in the later periods there are lower consumption, and in the last week the consumption is much lower. So, that is how the hyperbolic discounting or naive hyperbolic discounting model is able to explain the SNAP example. This is how the SNAP recipients consume more in period 1 than they had planned, leaving less for the future when they anticipated smoothing their consumption. In the following period, they again decide to consume more than they had planned to in either of the previous periods, again putting off consumption smoothing until a later date. Recipients continue to put off smoothing until they reach a point where they no longer have enough food to last the rest of the month and their consumption is forced to drop off significantly. This is what we can show diagrammatically. This is the planned consumption, which is somewhat smoother as compared to the actual consumption, which is actually steeper. Ideally, it tries to show that the drop is much steeper. We will later compare the naive hyperbolic discounting graphically against discounted utility model, and that would actually show us very clearly that how steep or drastic the behavior of the naive hyperbolic discounter is when specifically faced with this kind of time inconsistent preferences. That is all for the current module. These are the references used. Thank you.